about another application of graph traversal algorithms. Next, we're going to talk about counting reachable vertices. Counting reachable vertices and edges. Now, you might ask, Dan, how the heck can you do that? Now, obviously, if you want to know how many vertices and edges you have, you can always keep track of that information. You can store it like an attribute if you'd like. However, suppose that I give you a big complex network or graph, and I want to know, say, how many friends do I have in my cluster, or say, our connected component, to be a bit more precise. So you can think of this like a social network, for example. You have all your friends in your social network, and I want to know how many friends do I have, and I don't have this pre-computed somewhere else. Likewise, I want to know how many connections exist between my friends in, say, a social network. We're going to talk about how we can compute that information. So we're going to presume this graph exists, and I'm going to show you how you can explore the graph to compute this information based on what we call depth first search and breadth first search. So I'll be showing you both of these in those contexts. So the big thing I really want you to observe about either one of these algorithms is that it doesn't matter which of the two. Either one will mark each one of the vertices / nodes at most once. So if we use that, we can use that information to count the vertices, presuming, because if we never attribute or count an unmarked vertex twice, we can ensure we're not going to be inaccurate with our count, as long as we explore everything that we can reach. So I'm just going to mention that notice that we visit each vertex once. And that happens when we mark the vertex, right? So this specifically happens when we do DFS. It's like when we mark it, we immediately start exploring from there. But in BFS, we would put it into a queue, and it would get its turn eventually. But that's the first time we visit it. So now that we have that information at our disposal, we can try to take depth first search, and we can always simplify it a little bit. Because notice that we never actually have to really, if we're counting, like say if I give you this graph here. Say I gave you one that looks just like this. Say this is my network of friends, okay? It's not very big. Although I'm always looking for more friends. So suppose that I wanted to count how many vertices are in this network or graph. So notice that I have 1, 2, 3, 4, 5, 6. And suppose that I would like to do this. Now, if I use depth first search, the way that I would do this is I would start off with some vertex. I'd mark it. And then I would consider my neighboring or incident edges here. So the incident edges here, so these are the edges that come out of that vertex. I consider each one of them. Whichever one will take me a little bit further, I continue my search that way. So it's like if I was to just decide to wrap some string around myself and go run through the jungle and go, ah, just run through the jungle. So the point is that suppose I consider this one. Now, I'm not going to label any of the edges like I've done previously, just to illustrate a point. So if I do this, I can visit this one, and then I consider my incident edges, and I don't know, I could pick any one. I could go this one right here if I want. I can notice that I would never go visiting somewhere I've already marked, right? But I could keep a running total or tally of how many I have. Like say I call it count, and so far it's 3, right? So suppose I were to take this route. Say I go to this incident edge. I would update this to 4, right? Because that's how many I'm going to mark. Then I consider my incident edges. Notice I wouldn't explore here, I wouldn't explore there, and I wouldn't explore there. I should mention when I go running into the jungle, I take a big stick of chalk and I put big X's all over wherever I've been. So I don't go down that way again. But the thing is, when I'm done examining where I am, I would walk backwards. I would spin myself around, raveling up that string to walk myself back, okay? So then I would go back this way, and then I would examine my other incident edges. Suppose that these ones are already examined, so I would go here. So now I would have 5. Notice I've considered all my edges. I would go back, I would ravel myself back up, go back over here. I would consider this one right here. Marked it, so I increment my counter. I consider all my incident edges, so I'm going to ravel myself up back over here. Then I'm going to ravel myself back up. And I would keep doing this until I get all the way back. All the way back. And notice that I'll end up with a count, and it doesn't matter if I label the edges or not, which is something that DFS cold turkey would do. So let me show you how this would look by simplifying depth first search. So here's the algorithm. So I'm going to call it count vert for counting vertices or nodes. So I have that as input. I'm going to take in a vertex u of the set of vertices of some graph g is equal to v. So I have my set of vertices, my set of edges. And as output, it's going to tell me the number of vertices reachable from u. So again, like I said, it's just like if I wanted to count up all the friends in my social network. Now, I must stress that the reason why I'm saying that as opposed to other people's social networks, it would be that there would be another what we'd call connected component, another potential forest if we were to look at the discovery edges. And well, another tree in a forest, sorry. So I'm getting a little excited here. This always gets me excited. So it would be the number of vertices reachable from u. So what is the first thing I told you we were going to do? We're going to mark the vertex, right? So we mark the vertex. I mark it. That's the first thing I do. I just put an X on it. I put that on there. And then I'm going to have a counter. Now you might ask, Dan, am I going to have like a variable that is, say, static, for example, for those that are programmers out there, that would keep up the counter? Now you could do something like that. However, what I would like to do is I'm just going to have it so it's going to recursively keep the track of how many there are. So I'm going to presume from my current point that I've counted myself. And then as I go exploring, I'm going to add more to this bucket or collection. So it's hello, hello. So for each one of the incident edges, I'm going to consider every one of my incident edges. So I have you, and I'm going to consider every one of my neighbors, okay? We're going to do that, and we're just going to do exactly what I just described a moment. Yeah, you check the neighbors, so we check those neighbors, and now we just want to only count them if they're not marked, right? So that's all we have to do. So if V is not marked, that's the only time we can advance our search, but that's also when we know we're going to have more stuff to count, right? So if our opposing endpoint, or V in our case, is not marked, that means we can advance our search. That means we're going to be more things we can count. So I'm going to update count to be count vert. Whatever the result of count vert is, for V, plus the current count I have. I'll get out of the way. And then I just simply return the count when I'm done. So you'll notice that I've written this recursively, but I must stress that the principles still apply regardless if you decide you want to write this iteratively or use a different graph traversal algorithm. I just adapted DFS. I like to keep it simple, you know. There's something pretty about a nice recursive algorithm. And that's it. That's how you can count all the vertices in a given connected component, because a connected component will be all the vertices reachable from my start vertex. So this is how I could count up all my friends in my social network if I didn't have that information. It's pretty interesting stuff, right? So you might say, Dan, what do you do about edges? What do you do about edges? So for the sake of variety, what I'm going to do next is I'm going to show you how you can use breadth first search instead to count the edges. Now, one thing I must stress is that edges, it's a little bit more, you have to be a little careful, okay? So with edges, there's something else you have to do a little bit more carefully. So first, you can get away without having to worry about the vertices. However, if you care about the running time of your graph traversal algorithm, it may make a difference. What I can do is I can just simply take this idea I had over here, where our first here, all I did was I ignored the edges. But now what I would do is I just take those into account, but I don't really care about what the edges are labeled as. I just care that I count it. But for the sake of maintaining the same time complexity, I'm going to also incorporate this idea of marking. So what we're going to do is I'm going to show you how I can adapt BFS to do this. So I'll just mention that likewise, we can count the number of edges, by labeling edges, and only counting unlabeled edges. So when they're unlabeled, that's the time to count them. So just as an example, let's do this with breadth first search. So let's take the same graph I had over there. Just because I want to be consistent with you. So let's see what happens. So suppose I start off at here. And what I want to do, and now I must stress that with BFS, we have a queue, right? We're going to have a queue. And just to make this easier for us to keep track of, I'm going to number the vertices. Going to number those vertices. So let's have a queue here. We're going to start it off at 1. So 1 gets placed in here after I mark it. So I've handed over to the goblin. The goblin's got, I got vertex 1. Yes. So we're going to take it away from the goblin now. So we're going to take it away from the goblin. We're going to dequeue it out of here. And we're going to consider our incident edges. So we're going to have a tally of how many edges we have. Remember, these are the interconnections between the vertices. So I am going to now increment this whenever I count an unlabeled edge. So in this case, I pull out 1 and I look at all my incident edges. I'm going to take 1 step into the graph. So I consider this edge here. I'm going to just label them with the word counted, just to keep it simple. So notice that I have counted 1 here. I'm going to mark 2. I'm going to NQ it, enter it into the rear of the queue. It's going at the back of the line. And then we consider each one of these. Now I must stress them again, as long as it's an incident edge, it doesn't matter which order you take them in. So the fact this is a 2 versus a 4 versus 3, it doesn't matter in terms of the algorithm. When you implement it, most times it'll be based on the index or how you store the vertices, what order they're in. So same idea here. I put in 4 into the queue, back of the line. I've already marked it. And that increments my counter. And same idea here. 3 goes in here. Increment my counter. And now we're done with 1. It's gone. It's gone, everybody. It's gone, everybody. The goblin's going to take 2. We're going to take it away from the goblin. We're going to try taking an extra step into the search to get away from the goblin, okay? So let's see. So now we got a 2 here. So now this one's already labeled, so I'm not going to count it. We have this edge. That's already marked, so we know we're not going to put 3 into the queue, right? I must stress, however, it doesn't make any difference if you did this, except it will make the algorithm take a bit longer. I'll have more about that later. So now I have 4 edges. Again, I don't have anything to place into the queue. Now we're up to 5 edges. And now we're done with 2. Next, let's go to 4. Goblin takes out 4. Let's take it away from the goblin and run it 1 step away in the search, okay? So let's see. This one, we haven't accounted for this yet. However, 3 is already has already been marked, so we know we don't need to examine that one. So now we're up to 1, 2, 3, 4, 5, 6. So far we're up to 6 edges. And now next, let's consider this edge. That's not in the queue yet, so let's put in 5 at the end of the line. Increment our counter. And let's do 6 next. So that goes up. Now we got 8. And now we're done with 4. And now let's pull out 3. So DQ 3. All of its incident edges are already labeled, right? So we're done with 3. So keep in mind, you would go through each one of these and see that they're not labeled or labeled. 5, same idea. 6, same idea. And we're done. So now I have 8 edges. And notice that I've just adapted my breadth per search to be capable of doing this. And all I really care about is that the edge is counted for. So I just label it. I don't care if it's a discovery or forward edge or a back edge or a cross edge. And well, BFS would be specifically in our cases forward edges or discovery edges or a cross edge. So let's write out what this would look like. And I'm going to adapt BFS for this just so you can see what we just did here. So I'll walk you through the thought process here. So here's the algorithm. We're going to call it count edges. And it's going to have a starting vertex we start at. The input and output, similar to what we have over there. So I'm just going to, for the brevity of time, we're just going to skip over that detail. The point is it's going to count all of the edges that are reachable from my start vertex. So these are going to be on endpoints of vertices I can reach. So in BFS standard, you're going to initialize an empty queue. We're going to start off with an empty queue. And then we're going to enqueue in the source or start vertex. We're going to enqueue that in. And then we're going to mark, let's mark U. Not you, I'm talking about that U. Then, while the queue is not empty, meaning that we still have a vertex that we have not yet processed all of its incident edges yet, we're going to do as follows. So while the queue is not empty, meaning that we have another vertex in line, if this is the case, we're going to do the following. So first we take out, remember this is like when I was saying about the goblin taking it out from the front. So we're going to process the vertex on the front of the line or our queue. So we're going to dequeue off the front of the queue. That's going to be V. And then we go through our incident edges. So for each edge, VW, we're going to do as follows. We're going to do the following. Now, we have to be a bit careful here because remember, we're trying to count the edges. Now, as I said previously, we're just going to allow it to still continue to mark vertices, which I think will be a good idea for us if we want to maintain the same time complexities, as I'm going to mention in a moment. We're going to check if that edge is not labeled, because we don't really care about it if it's not. If VW is not labeled, then let's proceed. Let's proceed now. So now we know VW is not labeled. So that means we're going to increment our count, right? Because we're going to label that edge. Oh yeah, there's one thing we haven't done. Remember, we still have our counter. This is something we need to add into our BFS. So we're going to put a counter in. Remember, we need our counter. So let's add that in here. It's important. Otherwise, we're not going to be able to count things. So let's see. We got a count. We're going to increment our count, right? Because we have a new unlabeled edge to consider. So we're going to increment that by 1. Then we're going to label it as counted. As counted. And then lastly, if the opposite endpoint, sorry, I'm getting very excited here. If the opposite endpoint, W, is marked, then we don't do anything with W, right? If it's not marked, however, that means we have more graph to explore. That means it's going to go right into that queue at the end. If W is not marked, then we got q.nq. So I'm going to nq in W, and we're going to mark it. Mark W. Now let's make sure I got all my closing curly braces, okay? Got 1, got 2, got 3, and I think I need a 4th one. 4, and at the very bottom after the 4th curly brace, we're going to return the count.